Today let us understand about Coriolis component of acceleration. As you know that for any 2 points on a rigid link, say link AB, rotating with an angular velocity omega and an angular acceleration alpha, the acceleration of any 2 points will be vector summation of 2 components of acceleration. One is centripetal component of acceleration, another one is tangential component of acceleration. Acceleration of A relative to B is vector summation of centripetal component of A relative to B and tangential component of A relative to B, where centripetal component of A relative to B is velocity of A relative to B square by length AB, whose direction is parallel to the link and towards downwards, that is towards A. Similarly, the tangential component of A relative to B is alpha into length AB, whose direction is perpendicular to the link AB and it is in accordance with alpha. Likewise, whenever a moving point which moves along an oscillating with link rotating with an angular velocity omega, then the moving point will have an acceleration known as Coriolis component of acceleration. For example, consider the crank and slotted lever mechanism, quick return motion mechanism. OC is the crank, a fixed link. CP is connecting rod. OQ is the slotted lever. CP is the connecting rod, rotates with an angular velocity omega and which rotates about C. As connecting rod CP rotates, the oscillating link OQ, slotted link OQ, oscillates between two extreme positions and this Q is connected to the ram. Here, M is a fixed point on an oscillating link, P is a moving point, P is a die block or piston which is subjected to slides in a slotted link, and M is fixed point on an oscillating link. At the given instant of time, as the sliding point P coincides with the fixed point M on an oscillating link, when it oscillates with an angular velocity omega, then the sliding point will have an acceleration known as Coriolis component of acceleration. Along with this, the sliding point will also have a sliding acceleration with respect to M. Therefore, when a moving point which moves on an oscillating link, the moving point will experience an acceleration known as Coriolis component of acceleration. Let us understand the magnitude and direction of Coriolis component of acceleration. Magnitude and direction of Coriolis component of acceleration. Consider a link OQ. M is fixed point and P is a sliding point. As the slotted lever oscillates with an angular velocity of omega, then the sliding point P will have two components of acceleration. One is Coriolis component and another one is sliding component. Thereby, at the given instant of time, the point M, which is a fixed point on an oscillating link, will have two accelerations, centripetal component of M relative to O and tangential component of M relative to O. Along with this, the sliding component P with respect to M, then it has two components, Coriolis component of P relative to M and sliding component of P relative to M. Thereby, the total acceleration of a moving point P will be vector summation of four quantities: centripetal component of M relative to O, tangential component of M relative to O and Coriolis component, sliding component of P relative to M, Coriolis component of P relative to M. The total acceleration of a moving point on an oscillating link will be vector summation of centripetal, tangential, sliding and Coriolis component, where centripetal component of M relative to O is the centripetal component V MO square by MO, direction parallel to link MO and downwards. Tangential component of MO is alpha of MO into MO, whose direction is perpendicular to MO. Sliding component of P relative to M is direction parallel to line of reciprocation. Lastly, Coriolis component of P relative to M can be determined using the formula 2V omega, whose direction is perpendicular to MO and it is in accordance with motion. And it is in accordance with motion of link. Here V stands for the velocity with which the slider which slides an oscillating link. Omega stands for the angular velocity with which the slotted lever OQ oscillates. Thank you. Friends, let us take an example of how to determine the Coriolis component of the moving element on an oscillating link with this example. Consider the crank and slotted lever quick return motion mechanism. The details of QRMM is shown in this figure. Link OA acts as a crank, fixed crank. EAB, the connecting rod, which rotates in clockwise direction. The angle subtended by connecting rod with respect to crank OA is 120 degrees. OC is a slotted lever which has a die block or a moving point B. M is a fixed point on the slotted lever OC. The end of the slotted lever is connected to the ram through a link tube CD. The dimensions of all the links are shown here. The connecting rod AB rotates in clockwise direction with a speed 60 rpm. Crank length is 100 mm long. Connecting rod of 400 mm. Connecting rod of 100 mm. Then oscillating link of 400 mm. Link tube of 150 mm. Determine the Coriolis component of point B, the moving point B, and acceleration of point B. As you know that whenever a moving body which moves or slides on an oscillating link, then the moving body will have an acceleration known as Coriolis component of acceleration. In the similar way as we solved in the previous problems, to solve this, very first step is to draw the configuration to suitable scale. How to construct the crank and slotted lever quick return motion mechanism for the given data with respect to some scale? Let us first draw a line, vertical line, as per the scale of the configuration diagram, equal to 250 mm. O and A is 250 mm. Show that OA is a fixed crank. Then fix the position of slider D, which is 450 mm above the point O. That means at a distance of 450 mm, draw one more horizontal line from O. Now, connecting rod AB makes an angle of 120 degrees with respect to crank. From A, draw a line at an angle of 120 degrees. On this line, measure a distance equal to 100 mm as per the scale of configuration diagram. Fix the point P. Now join OB and extend up to C whose distance is equal to 400 mm as per the scale of the configuration diagram, with the CD distance as a radius, with the C as center, cut an arc to represent the point D and show this is a ramp. Join this CD. Then OC is the slotted lever which has a die block. At the given instant of time, this slider or a die block at B coincides with the fixed point M. This is the configuration of the given crank and slotted lever quick return motion mechanism. Next step is to draw the velocity diagram. Before velocity diagram, I need to know the magnitude and direction of velocity of any one of the link of the given mechanism. Here, the driving link is the connecting rod AB. Therefore, velocity of connecting rod AB, velocity of B relative to A. Since A is fixed, it becomes an absolute. Absolute quantities are expressed with a single alphabet. VBA is equal to VB, that is equal to length into angular velocity. Substitute the values and you are going to get the magnitude of velocity of B relative to A. The direction of velocity of one point with respect to some other point on a link is always perpendicular and it is in accordance with the motion of the link. Therefore, in the configuration diagram, I will show the direction of VB. Next step is draw the velocity diagram to the suitable scale. To start with, fix the pole of velocity diagram. Therefore, I will fix pole as O. Pole represents all the fixed points of the mechanism. In the given mechanism, the fixed points are O and A. D is not fixed point because it is a slider. Therefore, at the pole represent O and A. Now consider the connecting rod AB. Velocity of B relative to A is perpendicular. Therefore, magnitude is known. With respect to the scale of the velocity diagram and for this magnitude value, in a direction perpendicular to AB, draw a line perpendicular to AB and fix the point B. Vector OB represents the velocity image of the connecting rod AB of quick return motion mechanism. Now consider at this instant of time OB, that means B is coinciding with M, therefore I will consider MO. Velocity of M relative to O is perpendicular. Therefore, through pole, draw a line perpendicular to OM. Direction is known, but magnitude is unknown. Now, as the connecting rod rotates, the oscillating link OC oscillates between two extreme positions. During this course of action, the die block, the piston, which slides inside the slotted lever at the given instant of time, that moving point comes and coincides with M. Therefore, moving point will have a sliding motion, sliding velocity. For all sliding members, the direction is parallel to line of reciprocation. Therefore, through B, draw a line parallel to MO. This parallel to MO intersects the perpendicular line at this point. Here I am going to get small m point. Therefore, vector OM represents the velocity image of the link MO. In the configuration diagram, C is the extension of slotted lever OM. Therefore, on the vector OM of velocity diagram, extend this in the same proportionate as the point C extends on OM extended. Therefore, I am going to get point C. This can be achieved using the relation OC by OM is equal to vector OC by vector OM. OC distance is known. OM you can measure from the configuration diagram. Vector OM from the velocity diagram you can measure and substitute the value. Finally, vector OC is equal to OC by OM into vector OM. Calculate this OC. Accordingly, from pole O, fix the point C. Therefore, vector OC represents the velocity image of the slotted lever OC. Now consider the link tube CD. Velocity of D relative to C is perpendicular as seen at C. Therefore, through C, draw a line perpendicular to CD. But D is a slider. Sliding members, the velocity is absolute. When it is absolute, it starts from pole. Through pole, draw a line parallel to line of reciprocation. Parallel to line of reciprocation. These two intersect at this point. Here I am going to get point D. CD vector represents the velocity image of link tube. Vector OD represents the velocity of slider D. Check all the points of the configuration are there in the velocity diagram or not. O, A, B, C, D and M. O, A, B, C, D and M. All the points are there. With this velocity diagram, now next step is to draw the acceleration diagram. We need the centripetal and tangential components of each of the links of the mechanism, so that the total acceleration of any link is the vector summation of centripetal and tangential components. Therefore, we need to prepare a table and find out the centripetal and tangential components. As usual, in the first column, the links, connecting rod AB, oscillating link OM, link tube CD, and there is a slider D. And link connecting rod AB of length is expressed in meters, CD expressed in meters, but OM, in the figure, OM distance is not given. But when you draw this configuration diagram, actually you measure OM from the configuration diagram, multiplied by scale of the configuration diagram will give the distance OM. Therefore, OM into scale, this is capital OM, that means from the configuration diagram. From the configuration diagram, measure it, multiplied by scale, keep this distance in meters, that is the length of OM. The third column is velocity. Velocity of AB already you have calculated, or it is VB, substitute there. Then velocity of OM is vector OM into scale of velocity diagram, measure OM, multiplied by scale of velocity diagram, substitute here. Then CD, vector CD into scale. Now centripetal component, velocity is known, length is known, use this formula, calculate the value. Similarly, the tangential component of acceleration of AB, here tangential component means angular acceleration is not given. He says that the AB is rotating with uniform speed of 60 rpm, therefore alpha is unknown, you cannot calculate the tangential component, this becomes 0. Whereas the total acceleration of AB, since it is vector summation of centripetal and tangential, where tangential component is 0, therefore total acceleration of link AB is the centripetal component itself. Similarly, for link OM, velocity is known, length is known, use this formula, calculate the centripetal component. But tangential component of OM is not 0. He has not specified that OM is oscillates with uniform speed. No. Therefore, there exists an angular acceleration of slotted lever. That magnitude is unknown. Therefore, write it as magnitude unknown, but direction perpendicular to link OM. In the similar way, for link CD, velocity is known, length is known, calculate the centripetal component magnitude. Now tangential component, again it is magnitude unknown, but direction perpendicular to link CD. The last component of the mechanism is slider D. D is a sliding point. For all sliding members, acceleration is absolute. Therefore, acceleration is absolute. Magnitude unknown, but direction is parallel to line of reciprocation. With this information, now let us construct the acceleration diagram for the given mechanism. To start with, as usual, first pole of the acceleration diagram is to be fixed. Pole of acceleration diagram is represented by O1. At the pole, mention the fixed points O and A. Therefore, O1, A1. Now consider the first link. First link is nothing but the AB. Acceleration of B relative to A is vector summation of centripetal and tangential, but tangential component is 0. The total acceleration is centripetal itself, whose magnitude is known, but direction of centripetal component of B relative to A is parallel and downwards. Therefore, draw a line parallel to AB and measure the distance equal to the centripetal component magnitude. Vector O1 B1 represents the total acceleration of link AB. Now, consider OM. OM is MO. Acceleration of OM is combination of vector summation of centripetal and tangential. Centripetal component of acceleration of M relative to O is known, whose direction is again parallel and downwards. Therefore, through pole, draw a line parallel to MO and fix the point X1 representing centripetal component of MO. Tangential component magnitude is unknown, but direction is perpendicular to OM. Therefore, through X1, draw a line perpendicular to MO. Magnitude is unknown, but direction is perpendicular. Leave as it is. Now, consider point B, the sliding point B or a moving point B, which moves along an oscillating link, and at the given instant of time, this moving point coincides with the fixed point M on the same link OC. There exists the point B has 4 components of acceleration. Acceleration of B is centripetal component of M relative to O, tangential component of M relative to O, sliding component of B relative to M, and Coriolis component of B relative to M. That means acceleration of moving point B is the vector summation of centripetal, tangential, sliding and Coriolis. Acceleration of B, when I speak with respect to single point, it understood that it is an absolute. When it is absolute, it has to be measured from the pole. Already vector O1 B1 represents the acceleration of point B. Now let us understand, AB is connecting rod. B is a point on connecting rod. Also, B is a point on oscillating link also. Therefore, already we have shown the total acceleration of point B with vector O1 B1 that represents the total acceleration of B. In this acceleration diagram, centripetal component of MO is already represented. Tangential component is also shown in direction. What else? I have 2 more components. That means this total acceleration is vector summation of 4 terms: centripetal, tangential, sliding and Coriolis. The resultant of all these 4 will be the total acceleration. Therefore, first I will find out what is Coriolis component of acceleration of B relative to M. As you know that magnitude of Coriolis component is 2V omega. That means 2 into V means velocity of B with respect to M. Omega is angular velocity of slotted lever MO. Now, this is equal to 2 into velocity of B relative to M is vector MB into scale of velocity diagram. Here in the velocity diagram, measure vector MB. Substitute the scale of velocity diagram. This product represents the velocity of sliding point. Similarly, angular velocity of MO. Angular velocity of MO is linear velocity divided by actual length. Linear velocity of MO divided by capital MO. This is equal to 2 into vector MB into scale into velocity of MO means vector OM into scale divided by actual length MO. With this, I can determine the magnitude of Coriolis component of B relative to M. Now the direction of this Coriolis component is perpendicular to the link OM. Therefore, in the acceleration diagram, since already I expressed the total acceleration of point B with the vector O1 B1, which is the vector summation of 4 quantities, therefore the resultant of these 4 will be the total acceleration. Hence, at B1 for this magnitude, I draw a line perpendicular to MO. Perpendicular to MO, passing through B1. Now I will measure the magnitude of Coriolis component with the scale of the acceleration diagram from B1 and I will fix up this point. This component is Coriolis component of B relative to M. Now, total acceleration O1 B1, which should be a vector summation of 4 quantities. Out of that, centripetal of MO, tangential of MO, Coriolis of BM, but what else? Sliding is existing. Sliding means through this point, sliding of B relative to M. That means sliding component of acceleration of B relative to M is parallel to line of reciprocation. Through this point, let this be Y1. Through this point Y1, draw a line parallel to line of reciprocation. Parallel to line of reciprocation. This parallel line and this perpendicular line intersect at this point. Here I am going to get the point as M1. M suffix 1. Now centripetal x1 to M1, tangential component of MO, M1 to Y1, sliding component of BM, Y1 to B1, Coriolis component of BM. Centripetal, tangential, sliding and Coriolis, the total vector summation of these 4 quantities will be total acceleration of B. Now, look at this figure. I will consider OM. Total acceleration of OM will be vector summation of centripetal and tangential. Here also, centripetal component of MO, tangential component of MO. The resultant of these two will be vector O1 M1. That means vector O1 M1 is the total acceleration of link MO, which is vector summation of centripetal and tangential components. Now, B is a moving point on a slotted lever. At the given instant of time, this moving point coincides with the fixed point M. Since moving point which slides on an oscillating link, moving point will have 4 accelerations: centripetal, tangential, sliding and Coriolis. That is also expressed in the acceleration diagram. Centripetal, tangential, sliding, Coriolis, the resultant like this. Now, this length is also over. Where is the point C? C is on the extension of OM. Therefore, in the acceleration diagram also, O1 M1 is extended in the same proportionate as in the actual configuration. Fix the point C1. Now I have the oscillating lever OC, as O1 C1 is the acceleration image of link OC. Coming to this third link, CD. Acceleration of D relative to C as seen at C is vector summation of centripetal and tangential components. Centripetal component magnitude is known, direction is parallel and towards C. Therefore, draw a line through C1, draw a line parallel to CD, and with this magnitude of centripetal component from C1 measure the distance. This is centripetal component of CD. Let this be point Z1. Vector C1 Z1 represents the centripetal component of CD, whose tangential component is known in only direction but magnitude is unknown, whose direction is perpendicular to the link CD. Therefore, through Z1, I draw a line perpendicular to CD. Direction is known, magnitude is unknown. Extend on either side. Leave as it is. Coming to the slidarity. For all sliding members, the acceleration is absolute. Therefore, whose direction is parallel to line of reciprocation, through pole O1, draw a line parallel to line of reciprocation. This parallel line and this perpendicular line intersect at this point. I am going to get point D1. Vector O1 D1 represents the acceleration of the slidarity. Vector Z1 D1 represents the tangential component of CD. Look at the figure. C1 Z1 centripetal component, Z1 D1 tangential component, centripetal, tangential. The resultant will be the total acceleration of link CD. Now check all the points are there in the diagram or not. A1, B1, C1, M1, D1. This is how the acceleration can be determined from the acceleration diagram, and Coriolis component is also measured. Lastly, step 6. He is asked to determine what is the Coriolis component of B. Coriolis component of B from the acceleration diagram, vector B1 Y1 into scale of the acceleration diagram. You can determine. The second bit is acceleration of B. Acceleration of B is vector O1 B1 into scale. This is how we can construct the acceleration diagram for a quick return motion mechanism. Whenever there is a moving point which slides on an oscillating link, then the moving point will have 4 quantities of accelerations: centripetal, tangential, sliding, and Coriolis component.